for subsystem 1. And again, the first one, let me draw the force analysis reactions here. So let me put into 4 segments. And to do this, this is our another wall. So we have to take the whole free rod diagram. So that means for this case, I remove the wall. Instead, I replace that constraint by reactant force here for subsystem 1, which is 900, because we take the force equilibrium in the horizontal directions. And now we can begin to draw our things here. So in any cross section in the first segment, we can see doesn't matter about the location of the segment, then this is 900, so here should be always is 900. So in the first segment, the force equal to 900 all the way down here. So that's 900. And now we move our selection of the cross section to the second segment. So that is like this. So here is 900, and here is our applied loading 300. So from here you can see that should be equal to 600, right? And so 600, so that would be here. And here there's a jump, discontinuity. Now go move on, and if we choose the cross section here, so that would be the same thing. So here is 900, and here is 300. So here, from here, you can see this is also 600. So that means here should be all the way to here. Right? Either there's a discontinuity in the geometry, but that won't affect the loading distributions. We simply look up the count. We simply count the force. And now we go to the move to the last one. So say go to here. So that will be the whole drawing. So here is 300, and here is 600, and here is 900. So from here, the force is 0. So this is 0 here. Okay? And now we put into our calculations delta at this end. That is the relative, be relative to this point and relative to this, and etc. So for this case, that will be the PL over EA of how many segments? 4 segments. From I equal to 1 to 4, right? In total, we have, say, let me call this is the first segment 1, 2, let me use the symbols here. 1, 2, 3, and 4. Okay, so that would be I equal to 1 to 4, something like this. So that would be equal to the first segment is force is 900 kilonewtons, and L is 0.15 meters. And E, let me use it, the symbols. Okay, that's a 200 GPa. And what is A? A is the 250 millimeter square. That is for first one. Okay, we keep adding up. Plus the second one. The second one, the force is 600. So 600 kilonewton. And the length is 1.5. And E, the same, 200 GPa, and A is 250 millimeter square. That is for the second segment here. And then we move on to the third one. The third one, force, is the same, 600 kilonewtons, and 0.15 meters, and E. Then A, for the third one, that is larger a little bit, so that is 400 millimeters squared. And the last one is 0 force multiplied with 0.15 meter, and E times 400 millimeters squared. That's it. For every single segment here, they are stretching. So they all have the same sign positive. Okay. So for this case, in total, so this will be equal to 1.125 times 10 to the 9 divided by E. Okay. And sorry, allow me to not implement E, just simply is that number. I follow up my lecture note. So this deformation is going rightward. Okay, basically that is going rightward. Data B, we found it. Now we come back to the subsystem 2. The subsystem 2 is such that the reaction force, RB, is to push back, prevent such deformation to occur because of the constraint. So it must go back by delta B. From here, again, we can utilize our techniques. In this way, you can see for this case, for the subsystem, we working on this case, we want to calculate, for example, delta B for the subsystem. Delta B is equal to R PL over EA for the segment I equal to how many? Right now here we have how many segments we can work on. So I equal to 1 to a certain segment, let me call it N. And likely you can tell N should be equal to 2 for this case, right? So again, the techniques is this. For the second question, we have to work on the segment by segment. So the same techniques, let me work on the force and the reactions. Okay? And again, to work on these things, let me take the free body diagram of the whole thing. So here should be equal to RB. So from here, you can easily tell throughout the whole system, the reaction force and the magnitude is equal to RB. But this RB is trying to compress, right? That be okay? Again, you can repeat the same technique. You select the free body diagram, you select the cross-section here, and then you select the cross-section here. You can reach the result quickly, very quickly. Okay. So with this one, then here we only have 2 segments. The first segment will be equal to this one, the first part, and force is equal to RB times L 0.15 meter and E times A. A is 250 meters squared. For the second one, let me get rid of this. Is RB times 0.3. Right?
Aren't you doing minus the compression?
Yes, and good questions. For all my exercise, I try to work on the magnitudes first, and then I kick in the sign at the very last step. Okay, but that's a good one. So this one is 0.3. Why the length is 0.3?
The whole section?
Yeah, because for the whole thing here, from here to here. Okay? And then this is E and times 400 millimeters squared. This is the magnitude, and this magnitude actually is to move back. This is our constraint, right? So this is going to move into that direction. Okay, now what we can do, for the two subsystems, moving rightward must be kicked back by the same amount. So in terms of the magnitude, this is the magnitude. This is the magnitude, and let me work on these things. So this will be equal to 1.95 times 10 to the 3 times RB divided by E. Okay, that is the magnitude, and this is moving leftward. So this is the magnitude, the both magnitude, that is for subsystem 1. And for subsystem 2, we have that magnitude that must be equal. Why they have to equal? Because of the constraint here, right? So the equal basically is the compatibility equation for this question. So we set up the two numbers equal, then that means here, let me write it down, 1.125 times to the 10.9, E equal to E times 1.95 times 10 to the 3 RB. So therefore, we can solve for RB equal to 577 kilonewtons. And again, pay attention to your unit. Okay? And then therefore, IA should be equal to 900 minus 577 equal to 323 kilonewtons.
And where's RA pointing again?
And RA is the force here. So for example, here we have, say, let me remove the constraint, and here is RA. RB, and this is RA. Reactions at point A.
Wait, which one's RA?
RA is the internal forces.
RA is the reaction at the other constraint here. Yes, RA is the reaction force. Why? Because you can see, by looking at this problem here, our system is like this. And this reaction force RB equal to 577. And here is 600. And here is 300. So RA is this one. Right? And 350. Are we okay? Yeah, that is a new, probably that's the new concept, and that is new from ES331. A little bit new, additional to your statics. And try to read the textbook and give a try. Probably you can give a try. Next time, coming back Friday, we're going to try is this. I'm going to try is here the constraint will replace by a gap. It's a little bit more complicated. Additional, we will still working on the same question.